Water at 1 bar and 50 degrees C enters an isentropic pump which supplies a steam generator operating at 100 bar. The temperature of the water at the steam generator outlet is 520 degrees C. It is accelerated through a nozzle with an isentropic efficiency of 90% to produce a steam jet for cleaning purposes. The pressure at the nozzle exit is 1 bar. What is the exit velocity of the jet? What are the power requirements of the pump if the flow rate is to be 0.5 kilograms per second? At what rate must heat be supplied to the steam generator? So this is an open system question with multiple components. So the first thing we want to do in the given information is just identify what those components are. So from the problem description, we see we have an isentropic pump, and then that feeds a steam generator, and then the outlet of the steam generator goes through the nozzle. So we've labeled the state points 1, 2, 3, and 4, and we've recognized that there's a work input to the pump and a heat transfer going into the steam generator. In terms of properties that we've been given, at the inlet of the pump we have 1 bar and 50 degrees C. The steam generator operates at 100 bar, so realize that means P2 and P3 are both 100 bar because the steam generator is a constant pressure device. And we also know that the temperature at the exit of the steam generator is 520 degrees, so that's at 0.3. The pressure at the exit of the nozzle is 1 bar, and the isentropic efficiency of the nozzle is 90%. So notice the isentropic efficiency of the pump is 100% because it's described as being isentropic. We also know that the substance is water, and there's a mass flow rate of 0.5 kilograms per second through this system. So what we've been asked to find is the speed at the nozzle exit, which is V4, the power required by the pump, W dot pump, and the rate of heat transfer into the steam generator, Q dot. The assumptions we'll be making along the way: this system is operating at steady state, adiabatic pump and nozzle, so no heat transfer between the pump and the nozzle and the surroundings. We're going to neglect potential energy everywhere. And the steam generator is operating at constant pressure. Our analysis is going to be based on conservation of energy for a control volume, and we're going to be applying this to multiple components. So this is the most general version. So in terms of our assumptions, because we're operating at steady state, the left-hand side will always be 0. When we're looking at the pump and the nozzle, the heat transfer will be 0. When we're looking at the steam generator and the nozzle, the work transfer will also be 0. And each of these only has a single inlet and a single exit, so we won't need the summations over the inlets or exits. When we apply the energy equation to the nozzle, it reduces to this. So the enthalpy at the inlet, H3, is equal to the enthalpy at the exit, H4, plus the kinetic energy at the exit. So that's all that's left of the energy equation when we apply it to the nozzle, because it's steady state, no heat or work transfer, no potential energy anywhere, and of course we've assumed the kinetic energy at the inlet of the nozzle is 0 as well. Now the problem with this is we can't solve for V4 right away because we don't know H4. We do know enough to get H3, we know pressure and a temperature there, but we don't know enough about 0.4 to get H4. So that's a problem. So what we're going to do is look at the isentropic nozzle first. So this is the real nozzle. Now we're writing exactly the same equation again, but for the isentropic nozzle. So temporarily assuming that the efficiency of the nozzle is 100%. So notice that we now have a subscript S on the exit enthalpy and on the exit kinetic energy. So H4S and V4S. So this is now the isentropic case. Notice the inlet, there's no change there, but the exit properties are going to be different for this isentropic nozzle than for the real nozzle. Now the reason that we're looking at the isentropic nozzle is because we can find this H4S, because at the hypothetical or the isentropic exit we have one extra property that we know. And what that is the entropy. So first of all, we go to point 3. We know the pressure is 100 bar and the temperature is 520 degrees C. So we can go to table A4 and get the enthalpy at the inlet and also the entropy. And the reason we also looked up the entropy is for the isentropic nozzle, S4S is equal to S3. So for the isentropic nozzle, the entropy change is 0. So we have a value for S4S, and we also know P4 is 1 bar. So that's our two properties, pressure and entropy, that we can use to look up the enthalpy at the exit of the isentropic nozzle. So we go to table A3 and we see that our particular value of entropy is between SF and SG. So that tells us that it's a mixture. So we'll use that entropy to calculate a quality. So the quality of 0.4S is S4S minus SF divided by SG minus SF. And we have all of these values of entropy. This is our S3 value, and this is SF and SG from table A3. So all of that tells us that the quality at the exit of the isentropic nozzle is 88.491%. Now we can use that quality to get the enthalpy at the exit. So H4S will be HF plus X4S times Hg minus Hf. And so what that works out to is 2415.54 kilojoules per kilogram. So we've been able to get the enthalpy at the exit of the isentropic nozzle because we had that extra property at the exit, the entropy. So now we can go back and solve for the velocity at the exit of the isentropic nozzle. And so that'll be 2 times the enthalpy change, 3425.1 minus 2415.54, and those are both in kilojoules per kilogram. So what we need to be very careful to do here before we do this calculation is we need to convert this to joules per kilogram. So we need to multiply this by 1,000 so that we have joules per kilogram, because that's what's required in order to get a velocity in meters per second. So we finish off that calculation and we find the isentropic nozzle would have a velocity of 1421 meters per second at its exit. Now we're not done yet though, because that's not the real nozzle. We still need to figure out V4, the velocity at the exit of the real nozzle. Well, to get that, we remember the definition of the isentropic efficiency of a nozzle. It's the kinetic energy at the real exit divided by the kinetic energy at the isentropic exit. In the definition, this is actually v squared over 2, but it's v squared over 2 in the numerator and the denominator, so the 2's just cancel out. So we can rearrange this and get V4. It's the square root of the isentropic efficiency times the isentropic exit velocity. And we have numbers for all of those. Our efficiency was 90%, so that's 0.9. That's our isentropic exit velocity. So the real exit is not quite as fast. It's 1348 meters per second. So our first conclusion here is that the speed at the exit of the nozzle is 1.35 kilometers per second. Next, we're going to take a look at the pump and see if we can figure out the power requirements of the pump. Remember that this pump is isentropic. Now, a very good way to calculate the work done by an isentropic pump, which is pumping a liquid, is to use the equation that we derived in class for the work transfer for a reversible process in an open system. And you may remember that that work on a per unit mass basis is minus the integral from 1 to 2 of V dP. Now, the reason that this is so useful for a liquid pump is because when we're pumping a liquid, we're taking a liquid and we're pressurizing it. So when we do that, it's going to stay a liquid. So it will be in a liquid for this entire process. And because it's a liquid, its specific volume is essentially constant. It'll change a tiny little bit, but we can safely assume that that V is constant. So that means it can come outside of the integral sign. And that means that this integral is very easy to evaluate. It's just minus v p2 minus p1. And we have all of this information, or we can get it out of the tables. So P1 is 1 bar and T1 is 50 degrees C. So table A3 will tell us that the specific volume is 1.0121 times 10 to the minus 3 meters cubed per kilogram. And while we're there, we might as well look up the enthalpy because we'll need that later. And that's 209.33. So we can use this to calculate the power input to the pump. So realize that the power that the pump requires is equal to the mass flow rate through the pump times the work per unit mass. And so using the equation we just came up with, here's our mass flow rate, 0.5 kilograms per second, the specific volume, the pressure at the exit of the pump, being careful to write that in kPa, and the pressure at the inlet of the pump, also in kPa. So we do that calculation, we find that W dot P works out to minus 5.099 kilowatts. And notice that it makes sense that this is negative because it's a work transfer going into the system, work done on the system. So we can write our conclusion here that the power required by the pump is 5.01 kilowatts. Now the last thing that we need to do is calculate the heat transfer going into the steam generator. Now, if we take a look at the properties that we know, we'll realize we don't know the enthalpy going into the steam generator. And we're going to need that to calculate the heat transfer going into the steam generator. So before we leave the pump, we're going to use the first law applied to the pump to get the enthalpy at the exit of the pump. Notice that we haven't used the first law for the pump yet. Instead, we calculated the work for the pump directly from minus the integral of v dp. So we can return to the pump now and write the first law for the pump, not to find the work transfer because we already know that, but to calculate the enthalpy at its exit. So that's what we're going to do next. So in order to determine the heat added in the steam generator, the enthalpy at its inlet is required. And this can be determined by applying the first law to the pump. So when we apply our first law to the pump, we get the power of the pump equals minus m dot h1 minus h2. And we know everything in this equation except h2. So here we've just rearranged it to solve for h2. And we put the numbers in, so 209.33. Remember we looked up h1 back here. Put that in there. This is the power that we found for the pump. Notice it's negative, but there's also a negative in this equation, so that gives us a positive, and then divided by mass flow rate. So that gives us the enthalpy at the exit of the pump, which is the enthalpy at the inlet to the steam generator, 219.35. So now we can take a look at the first law for the steam generator, and that's going to tell us that the rate at which heat is added in the steam generator is the mass flow rate through it, times H3 minus H2, the enthalpy at the exit minus the enthalpy at the inlet. And we know everything on the right-hand side of this equation. 0.5 kilograms per second, 3425.1 kilojoules per kilogram at the exit, and 219.35 kilojoules per kilogram at the inlet. So that tells us the rate at which heat is added is 1602.9 kilowatts. So our final conclusion then is the rate that heat is added in the steam generator is 1.60 megawatts.